This lecture will be talking about generalized linear models. Specifically, we want to talk about describing general linear models and the different components that make up a GLM. We will review the Poisson GLM model and then review how we interpret the output from a generalized linear model. Let's start with why we even need a generalized linear model. So if you recall from a regression, if we have the data points that we see here in blue, what we are doing with regression is we are trying to fit a line that minimizes the sum of squared errors and our expected value of y to fall on this purple line that you see here. The mean is going to fall right on the line, and the errors are expected to be normally distributed around that mean. And so that's what we see here. So what happens if we have a situation where this is not the case? What if, for example, you assume that you need to predict a number of defective products, which would be your y variable, with a sensor value, which is your x, as the explanatory variable? The scatter plot looks something like this, and so we'll see that here in blue. So there are a few problems that we have when we try to use simple linear regression on this. The first problem is the relationship between x and y doesn't seem to be linear, and it's going to be more of that exponential type of relationship. Another problem we have is the variance of y does not look constant throughout all of our x values. You can see that as x increases, the variance is also increasing. That's going to be a problem when we have simple linear regression. The third problem is, as y represents the number of products, it always has to be a positive integer value. So 1, 2, 3, and even 0. However, the normal distribution needs for linear regression to assume that it can be a continuous variable and that it can have, for example, 0.2, which would not make sense within the context of this problem. You can't have 0.2 defects. So it needs to be an integer equal to or greater than 0. So how do we solve this problem? Okay, so GLM can come to the rescue. In this example, we are going to go into more detail, just trying to give you a high-level overview. What we are doing is using a link function. We are using a log link function specifically to connect a linear product to a set of your y observations. The linear predictor is just a linear combination of your parameters. So here you have a beta 0, beta 1 with x1 being your explanatory variable. And the linked function literally links the linear predictor and the parameter for probability distribution. So in the case of a Poisson regression, the typical link function that we would want to use is a log link function. This is because the parameter for a Poisson regression must be positive. The last component here is the probability distribution that will generate the observed variable, and in this case would be y. As we are going to use, in this case, the Poisson regression, we're looking at the Poisson distribution. So that's just kind of the general layout of how a GLM will work. Now that we have had a brief introduction on GLM using a Poisson distribution, let's go into it a little bit more formally. So generalized linear models are a general class of linear models that are made up of three components. We have a random component, a systematic component, and a link function. Okay? The random component identifies the dependent variable y and its probability distribution. In that last example, we were using the Poisson distribution. There is the systematic component that identifies a set of explanatory variables that can be explained by x sub 1 through x sub k. And these are our x variables that we will be using. Then we have the link function, which identifies a function of the mean that is linear function of the explanatory variables. So as we've shown below, using that equation. So let's go into our random component first. So far, the regression models that we have fit are simple and multiple linear regression, They assume that there's a conditionally normally distributed response with a constant standard deviation. When we have binary outcomes, such as success or failure, that random component also has a binomial distribution, and the model is called a logistic regression. When you have count data, the number of events is fixed, or it could be also a length of time that is fixed, and you run the random component using the Poisson distribution. So when you have the Poisson distribution, you have a Poisson regression. When your count data has a variance V of Y, and it is greater than the expected variance, or E of Y, the model we would fit would be a negative binomial distribution. And then continuous data with a skewed distribution and variance that increases with the mean can be modeled with a gamma distribution. So now let's discuss some of the common link functions. The first one that you have is the identity link, which is used in normal and gamma regressions. Then the log link function is used when the mean cannot be negative, as well as when the data that you have are Poisson counts. And then you have the logit link, and that's used when the mu or the mean is bounded between 0 and 1, as we've seen with the binary type of data. Going into logistic regression, a logistic regression is when you have a dichotomous or binary response variable and numeric and or categorical explanatory variables or variables. So here the goal is to model the probability of a particular outcome as a function of the predictive variables. And again, here the probabilities need to be bounded between 0 and 1. So in this case, the distribution of responses can be binomial because it's a binary outcome. And so the link function that we use here would be the logit function. Now for a Poisson regression, generally it is used when you have count data and when the distribution is going to follow a Poisson distribution. One of the restrictions that we have with a Poisson distribution is that we expect the value of y to be equal to the variance of y. So the mean and the variance are going to be equal, and that's by definition from the Poisson distribution. So then the link function can then be the identity link. But typically, you'll still use the log link function. Then tests are conducted using the logistic regression, but when the mean and the variance are not equal, that's a condition that we call over-dispersion. And oftentimes, the Poisson distribution is going to be replaced by a negative binomial distribution. So again, you will have this if your mean and your variance aren't equal. So typically, you will see this when your variance is higher than your mean. And in that situation, you'll want to use a negative binomial distribution instead of that Poisson distribution. Continuing with Poisson distributions, a response is a count. So it's assumed to have that Poisson distribution with a positive mean, or mu. You assume that the log of mu is a linear function of the covariance. Another way of thinking about this is that your mean is the exponentiated amount of your linear function of covariance, or the exponent of the inside of your formula. So Poisson is going to be a standard distribution that we will use when we are dealing with count type of data. Here is the probability distribution, what it looks like for Poisson. The count y must have values that are integer, so 0, 1, 2, 3, and so forth. And therefore, we have to have a mean with a positive value. Now, looking at the regression model, the response y, covariance x1 to x sub k, has a Poisson distribution with a mean of mu. The mean mu is related to the covariance by the log of the mean being equal to the inside of that formula that's seen here. So similar to logistic regression, the parameters are estimated by the maximum likelihood estimation process. Going back to the data from earlier in the presentation, the blue dots are what were shown earlier. And so if we fit a Poisson regression to this set of data, we end up with this purple line as our predicted values. And then the added bar plot of the probability mass function of a Poisson distribution was also added so that we could look at how it would be different from what was shown earlier when it was assumed that we had normally distributed data, as in the case that we would have with simple linear regression. So here you can see there's a difference, and it's going to be a better fit to what we see with this particular data set and when we're dealing with this particular problem. Now let's talk about the interpretation of the beta coefficients within the context of the Poisson regression. So if your beta is greater than 0, that means the mean increases as the x value increases, and when it is less than 0, it's going to decrease. So a unit increase in x changes the mean by a factor of the exponent of the beta. You're going to have to exponentiate the beta, and that is the increase. So it's like the odds that are discussed in logistic regression, where you need to exponentiate it to see what the effect it is on your y value. So when we estimate our betas, we use the maximum likelihood like we did in logistic regression. So the basic idea is that when we use the Poisson distribution, we can work out the probability of getting any particular set of responses, which is that value. In particular, we can work out the probability of getting the data that we actually observe, and this is called the likelihood. And then we choose our betas to maximize the probability, or the equivalent, the log likelihood.